Welcome back to our video series on quantum computing. In the last episode, we unlocked the door to the revolutionary world of quantum computers and discovered why they can tackle problems that classical machines wouldn't dare to approach. Today, we are stepping deeper into this quantum realm to explore its building blocks, qubits and quantum gates. What makes a qubit such a marvel? And how do quantum gates choreograph their mysterious dance to perform computations that defy classical logic? This journey will uncover the science, engineering, and the sigil behind the machines driving this quantum revolution. In 2019, IBM unveiled their quantum computer at a consumer electronics show in Las Vegas, captivating audiences with its futuristic promise. During a demonstration, a journalist blurted out, "So, it's like Schrödinger's cat, but for computers?" And yes, that's exactly it. A qubit state remains a delicate mystery, undecided until measured, much like the famous thought experiment of a cat that's both alive and dead at once. Let's unravel this quantum mystery. Qubit is not just a classical bit that can only be in any one of two states, 0 or 1. Instead, it can exist in a state that's 1, 0, or both at the same time, in a superposition of these states. Mathematically, a qubit is represented as a vector in a two-dimensional complex vector space. This vector, psi, is a linear combination or superposition of the states 0 and 1. The coefficients of these states, often denoted as alpha and beta, are complex numbers. Their squared magnitudes, alpha squared and beta squared, represent the probabilities of measuring the qubit in states 0 and 1, respectively. To ensure total probability of the qubit state being 100%, alpha squared plus beta squared equals 1. Qubit can also be visualized using the Bloch Sphere, a 3D representation that brings its quantum nature to life. Imagine a sphere where every point on the surface represents a possible qubit state. The north pole on z-axis corresponds to state 0, while the south pole to state 1, and every other point in between signifies the infinite possibilities of superposition of these states. A qubit becomes a traveler on this sphere, guided by two angles, theta and phi, which determine its precise position. But here's the fascinating twist. Superposition is just the beginning. The true magic of qubits emerges when they start interacting with each other. To choreograph this quantum interplay, we need quantum gates. This is where the real story unfolds. Quantum gates transform quantum computing from concept to reality. Unlike classical gates, like AND or NOR, which rigidly flip bits between 0 and 1, quantum gates act like choreographers, orchestrating the qubit's multidimensional movements. They don't just flip a state. They adjust probabilities, change phases, and even create entanglement between qubits. Mathematically, each quantum gate corresponds to a specific operation on the qubit's state vector. The transformation is represented as a unitary matrix U. For a single qubit, this is written as psi is the pre-altered qubit which is being operated with quantum gate, or the unitary matrix U, to give the transformed qubit state of psi dash. The term unitary means that the gate preserves probabilities, satisfying the earlier mentioned rule that alpha squared plus beta squared equals 1. This ensures that no information is lost during the transformation, making quantum gates both precise and powerful tools for manipulating qubits in ways classical computing could never achieve. Now, let's understand the various types of quantum gates. Imagine flipping a coin that lands perfectly balanced on its edge. This is the essence of the Hadamard gate or H-gate. This is a single qubit gate which takes a qubit in a definite state, 0 or 1, and puts it into superposition, with equal probability of being measured as 0 or 1. That is, the qubit now has a 50% chance of being 0 and a 50% chance of being 1 when measured. It's the ultimate gesture of uncertainty, but in the quantum world, uncertainty is power. Mathematically, the Hadamard gate is represented by the matrix H. Geometrically, This matrix operation rotates the state vector from the z-axis to the x-axis on the Bloch sphere by 90 degrees or by pi by 2 radians in the counterclockwise direction. Hadamard gates are crucial for initializing qubits into superposition for exploration in many quantum algorithms like Grover's search or quantum Fourier transforms. Without this, quantum computers cannot fully leverage superposition to process multiple possibilities simultaneously. Now let's introduce the CNOT gate, or controlled NOT gate. This quantum gate operates on two qubits, identified as control qubit and target qubit. CNOT is a type of NOT gate, but slightly different. It performs the NOT operation only under a specific condition. As shown in the symbol of CNOT gate, it has two inputs and two outputs. The upper input pin represents the control bit that specifies the condition which determines whether the gate should perform NOT operation or not. The lower input pin indicates the bit that is the target for NOT operation. Now let's look at the CNOT gate, state transformations. If the control qubit is in state 0 or non-operational, the target qubit remains unchanged. If the control qubit is in state 1 or operational, the CNOT gate flips the target qubit. 0 becomes 1 and 1 becomes 0. For clarity purposes, you can see the impact in red and green color. The controlled NOT gate illustrates the concept of entanglement of qubits. The state of the target qubit depends on the control qubit, no matter how far apart they are. A phenomenon in quantum mechanics, which Einstein referred to as spooky action at a distance. Since this gate operates on two qubits, mathematically, it is represented by the unitary matrix in 4x4 dimensions. This quantum gate is indispensable for algorithms requiring entanglement, such as Grover's optimization algorithm or Shor's cryptographic computations. Moving on, allow me to introduce the next set of quantum gates, the Pauli gates. Named after one of my favorite physicists, Wolfgang Pauli, these gates are a cornerstone of quantum operations. The Pauli gates are like the architects of rotation, manipulating qubits by spinning them around different axes in their quantum state. There are three types of Pauli gates, each represented by a unique Pauli matrix, X, Y, and Z. Together, they form a powerful toolkit for performing one-qubit operations, enabling precise control over a qubit's position on the Bloch sphere. Whether it's flipping a qubit state, shifting its phase, or combining these effects, the Pauli gates unlock an entirely new level of quantum manipulation. These three gates include X gate. This gate acts like the classical NOT gate, flipping the qubit state from 0 to 1 and vice versa. As can be seen from the figure, it rotates the state around the x-axis of the Bloch sphere by pi radians or by 180 degrees. Z gate. The Z gate imparts a phase flip to the qubit state, leaving the basis states 0 and 1 unchanged, but inverting the relative phase of 1, it rotates the qubit state around the z-axis of the Bloch sphere by pi radians or by 180 degrees. Y gate. The Y gate is a combination of X and Z gates. It applies both a bit flip and a phase flip to the qubit. It rotates the qubit state around the y-axis of the Bloch sphere by pi radians or by 180 degrees. Quantum algorithms rely on combinations of all these gates to construct quantum circuits. For example, Hadamard gate or H gate initialize qubits into superposition, often the starting point for unleashing the power of quantum algorithms. This is a key step for algorithms like Grover's search or the quantum Fourier transform, where exploration across many possibilities simultaneously is essential. Controlled NOT gates or CNOT gates causes entanglement of qubits, a phenomenon where qubits become deeply interconnected. This gate is pivotal in algorithms requiring such quantum collaboration, including Grover's optimization and Shor's algorithm for cracking cryptographic codes. Pauli gates adjust states or phases of qubits for fine-tuned computations. They act as precision tools in quantum manipulation, enabling precise qubit control, modifying angle theta and phi in the Say equation. Now, think about quantum cryptography, an area where these gates demonstrate their full potential. How do we send information without the fear of being hacked or intercepted? Here, quantum circuits can perform secure key exchanges. What makes this so powerful? Any attempt by an eavesdropper to intercept the communication would disturb the quantum states, making their intrusion detectable. It's an elegant marriage of physics and computation, ensuring unparalleled security in the digital age. As we wrap up this exploration of qubits and quantum gates, we've seen how these extraordinary tools redefine the limits of computation, laying the foundation for a future powered by quantum machines. But every revolution has its origins. How did visionary ideas evolve into the quantum computers of today? And what milestones have paved the way for the machines shaping tomorrow? In the next video, we'll journey through the fascinating history of quantum computing and uncover the latest advancements driving this field forward. Stay curious and make sure to subscribe and press the bell icon as we continue to unlock the secrets of the quantum world. The future awaits.